Hello and welcome to day one of microterm 2. We're talking about probability this microterm. And this is section 1.1. We're going to start off looking at a little bit of set theory just to kind of get an idea of some things that we've actually talked about quite a while ago. I'm thinking like 5th or 6th grade, and is often overlooked, but is kind of used in probability just as a kind of starting point. So that's the way we're going to use it, and let's see how we can do here. So a couple of questions. First of all, what is a set? So we're talking about the introduction of sets. And so what is a set? So the definition, the mathematical definition of a set is an unordered collection of items. Okay, just an unordered collection of items. So we could have things like, they don't even have to necessarily be related, but if they are, then it kind of sets a little bit of an idea of what we're working with. We could have something like Toyota, Honda, throw a Ford in there, and a Chevy. Okay, that's a collection of items, and in no order. And really, the unordered part doesn't mean that they can't be written in order. It doesn't mean that they can't. Maybe you want to write them in alphabetical order just to make it make sense for you, or in numerical order just to make sense to you. And I did forget something. Sorry. So an unordered collection of distinct items. Okay, and the distinct items idea just means that I can't have two of the same thing in a set. Okay. But again, the unordered part just means that the order doesn't matter. It means that they can be in order, but that doesn't allude to anything. That doesn't make anything more likely to be around than another. Okay. And whenever we write sets, we always want to put them in, I guess I could make my first one okay. We want to write them in these curly braces. That's what they're called. Okay. And it's that symbol on a keyboard. It looks like this. Okay. We would want to write our sets in between these symbols. Okay. Now, I will warn you that mine start to look very sloppy as I'm trying to write sets quickly. So be prepared for that, and just understand what it is when I bring it up. So the next question is it a set or not? The first one, I have -3, 2, 7, and 11. And notice they are in numerical order. And so it's not that it breaks a rule when it's in numerical order. It just doesn't hold any meaning to it. The order of the numbers in there doesn't hold any meaning. So this is a set, and they're all distinct items. Okay, it's a collection of them. So yeah, it fits. The next one, 1, 5, 5, 7, 9. This one is actually not a set because it is not a collection of distinct items. Because 5 is repeated, that in essence brings some order or some weight to the 5 that we don't want to know about. So it's not a set. Now, if we left out one of those 5s, then it would be okay. But since the 5 is repeated, it's no longer a set by the mathematical definition. The last one, apple, banana, blueberry, bread. They're not necessarily connected at all. I mean, yeah, they're all food, but but I've got a couple of fruits, I got a grain. None of that matters. Okay, nothing is repeated. It's a collection of items, so it is a set. Okay. Now what I want to do is I want to start talking about our number sets. okay, are sets of real numbers. And just so we know what they are so we can use them in the future. The first one is the natural numbers. And this set looks like this. It starts at not 0. Way to be wrong on the first thing you write. Good job. 1, 2, 3, and so on. Okay. The way I think about the natural numbers is they're the numbers that we start counting with. And now, then I always get, I always ask the question like, well, is 500 a natural number? And yes, it is. Okay. Even though when I was a little kid, I probably didn't count to it, I could have with the skills that I had. Okay. Once I know how to count to 100, I can pretty much do anything. Okay. So I could have counted to 500. It could be in there. Okay. So natural numbers just start at 1. They're the non-decimal, non-fraction numbers from 1 on to infinity. And we use n as the symbol for it, but we put a double bar on the first leg. Okay. So you'll see this set abbreviated this way throughout a lot of the things we do. Okay, the whole numbers, the only difference between the natural numbers and the whole numbers is the number with a hole in it. It starts at 0, then 1, then 2, then 3, and goes on forever. Okay, we use a W for whole numbers, and we double bar the first line. The next set is the integers. The integers is weird. The set of integers is weird for a couple reasons. Number one, it doesn't have a starting point. Technically, it starts at negative infinity and then goes -2, -1, 0, 1, 2, and so on. Doesn't have a starting point, doesn't have an ending point that we can actually write down because you can always come up with the next biggest number or the next smallest number. Another reason the integers is weird has something to do with how you say the word number in a different language. But you'd think we probably use an I for this. That would kind of fit the pattern. But we don't. We use a Z. And we double bar the vertical leg. The next set we have is the rational numbers. Now, rational numbers, that's where we start dealing with decimals and fractions. There's still no starting point, and it's pretty tough to even write all of these, but I'm going to go all the way to -1, maybe say -1/2, -1/3, -1/4, and then 0. And there's numbers in between these, so this is a really hard one to write out all the elements of. So we've got 1, we've got 2.5, we've got, let's throw, no, can't do that. Let's throw 3.3 repeating in there, and so on. Okay, so since that's such a tough set to write, we actually write it a different way. And we write it in what we call set builder notation. So there's multiple ways to write a set. You can either list all the elements or list enough elements like we've done in these ones until we get some sort of a pattern that's going to continue. This one doesn't really have a pattern. It's just all whole numbers, decimals, fractions, and kind of easy on the decimals, I guess. But decimals that end or repeat are the rational numbers. So the way we actually write it is we talk about set builder notation. I want it to be all x such that, actually I think I'm not going to use that vertical line. I think I'm going to use the colon that I used in class, such that x is equal to some fraction, because any whole number, any fraction, any decimal that ends or repeats can be written as a division problem. so the set of all x such that x is equal to p over q, where p and q belong to the integers. And there's another requirement, and it's that q is not equal to 0. So if I could have fit all that on one line, I would have, but I couldn't, so I didn't. And so this is called set builder notation. And there's a couple things in here that I said that may not be too obvious. This, the two dots here, just the, like what's in between the hours and the minutes on a clock, on a digital clock, a colon is what it's called in English, is the math way to say such that. Okay, where x is equal to p over q, we know what fractions are. Where p and q, and then this weird looking e. Okay, this weird looking e is another thing that's probably new to us. It's the math symbol way to say belongs to. Kind of gives some ownership of some things. Okay, so that says where p and q belong to, the z comes from the integers that we saw last time. So where those two numbers are integers, positive or negative, whole numbers with no decimal or fraction part. Okay, and then q is not 0. That's just because we can't divide by 0. Okay, so this whole thing is called set builder notation, and it's a way to encompass a lot more than being able to just, we can't list all those numbers, so we have to find another way to say that. Now, another weird thing about the rational numbers is that we use the letter Q with kind of double barring that left-hand side. We use the letter Q to stand for the integers. Sorry, the rational numbers. Okay. And my best guess is Q quotient. Quotient is the answer to a division problem, and this requires some division problem stuff. Okay, so that's why I think it's a Q. The next set that we have are the irrational numbers. Okay, this is where we get to use our I, and we double bar the first one. It actually looks like the Roman numeral 2. And it's the best way you can describe it is any number that is not, my pen's lagging out a little bit, that is not rational. Okay, that is not rational. So if it doesn't fit into this set, then it's an irrational number. Some examples that we have, and we're not limited to this, but something like the square root of 2. Okay, the square root of 2 is a decimal that never ends, never repeats. Just has a strange pattern all the way through. Probably the most famous one is pi, 3.1415, blah, 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 blah. There's also another number e that's similar to pi, but it's like 2.71. That's also an irrational number. Okay, and we're not limited to those, but those are 3 of them. And then, any combinations of those. Realistically, any square roots that aren't perfect squares are irrational numbers. So like the square root of 5 is an irrational number. Okay. All right. Then we have 2 special sets that aren't related to these. We have the empty set, which we mathematically denote as a 0 with a slash through it. It's the set of nothing. I'm going to say the set of no elements. Okay. Elements are usually, the word element relates to an item in a set. So an empty set is a set with no elements. Okay. The universal set, which can realistically change based on what you're thinking about, what you're working with, is the opposite of the empty set. It's the set with all elements. Okay, set with all elements. And as I said, this can kind of change based on what you're trying to work with. If we were trying to work with real numbers, the most common one in high school math classes would be the set of all real numbers, okay, which is a combination of the irrationals and the rationals together. And that would be typically our universal set. That's more of an example than the notation, so I'm going to put it over here. If we're defining a universal set, we're going to use the letter U with a double bar on the start. Okay. Now we've got some symbols in our set theory stuff that can kind of help us look at some different things. If we just use a capital letter, no special lines on it anywhere, that's meaning a set. Okay, we would call a set a certain letter so that we could recall that really easily. So we could say like, let's let A be 2468. Okay. Now, if we put a little c in the superscript, like in where we'd put an exponent, or if we put a line over A, we mean the complement. That's the word for it. The complement of A, which just means everything that isn't A. I'm just going to say, to be a little bit quick about it, not A. Okay, but it's everything that's in the universal set that's not in A. So if I was living in the natural number universe, so let's just say I just had the natural numbers, 1, 2, 3, 4, 5, and so on. If I looked at not A, not this A, then the only numbers that would be in A complement would be 1, 3, 5, 7, 9, 10, 11, 12, 13, and so on, right? So some easier ones to think about is if I'm looking at the set of the even numbers, the complement would be the set of the odd numbers, unless I had decimals and fractions, but it's just the opposite of A. Okay, here's the symbol again. It means belongs to, or is an element of. That's another way you could say it, is to say that this is an element of. And so kind of an example, we might say like 0 is an element of the integers. Okay. If we put a line through it, it means doesn't belong to. And so for that, we might say, well, let's stick with 0. 0 isn't an element of the natural numbers because the natural numbers start at 1. So 0 isn't a natural number. These next ones, I'm just going to say what they mean, and then we'll kind of look at what that is a little bit closer on the back. Okay. This first one looks like a C with a line under it, means a subset. Okay, a subset. We might say like A is a subset of B, just for notation. If there is no line under it, it means proper subset. And these two are connected, and I'll talk about what that means, but these two are connected kind of like the inequalities that they kind of look like. If you remember inequalities, we had this one and this one, which this one means less than or equal to, this one just means less than. And the line underneath meant the or equal to. It means like you could say that 1 is less than or equal to 1. Okay? But 1 isn't less than 1 because it's equal to. So that part doesn't work. Okay? And same thing kind of applies here. This one, going the other way, the opposite of a subset would be a superset. And this one would be a proper superset. Let's go ahead and flip it over and look at a little bit more on the definitions of these. For something to be a subset of something else, and I'm going to do this kind of within a very general example. If A is a subset of B, that means that everything in A, every element of A, is in B. Okay? And even up to the extreme case where every element of B is in A, kind of thinking of it backwards, where, let's say A was 0, 1, 2, 3, and B was 0, 1, 2, 3, those would still be subsets. For a proper subset, the only difference is A can't be exactly B. Okay, it gets rid of the or equal to part. Okay, for a superset, and make sure you don't try to make it look like an inequality, it should be rounded. If A is a superset of B, it means that quite the opposite. Every element of B is in A. And then proper superset, same idea. If A is a superset of B, then B can't be exactly A. And for these two, what it really means is that there has to be, like in this one, there has to be something that's in B that's not in A. And here there has to be something that's in A that's not in B. Okay. Down here, I think this is all practice. So I want you to give these a shot and then check them with me. And otherwise, hope you have a great day, and we will see you in class.